That definitely. So hopefully you will enjoy this presentation, and please let me know if you got any questions, obviously, at the end. Just as mentioned by Jaco, one of the things is that we're approaching the subject of ammonia as a combustion fuel. And in that sense, how it can be used to combust systems in internal combustion engines, furnaces, gas turbines, and propulsion systems. Some of the work that we've been doing, Some of the work that we've been doing relates to all these components, but also we are looking into public perception, and I will mention about it a little bit. These are the contents of my presentation. And this is just a little bit about myself. I've been working on this subject for almost 7 years with different projects, different panels, Royal Society policy briefings, etc. Things that again go back to all the different complexities that ammonia has to offer as a combustion fuel. Just as raised by hands, and this is where I'll start my discussion about, is we're talking about renewables and then bringing all that energy to reduce greenhouse gases. Now we know already that these systems are very intermittent, and this is just something that is obvious not only because we know that sun goes and disappears, especially here in the region where we're in Northern Europe, but also in places like, for example, Australia. So what happened a few years ago was Australia lost power for almost 2 weeks. They had blackouts, and this was because they were relying on alternative energies at the moment and batteries that were not coping with the demand that they had at the moment. Just a year and a half ago, 2 years ago, here in the UK, we suffered something similar. All the region of the Midlands suffered a blackout of almost 1 million people losing power, and that was because of the day we were running almost at 50% wind power, which just takes us back to then thinking we need to store some of that energy if we want to then have a reliable, independent power grid. And obviously, many things come back to mind, and just on the basis of what Hans mentioned, we've got all these different ways of storing energy, from batteries, chemicals, and obviously compressed gas. But from our purpose, again, thinking about chemicals, ammonia is one of the ways forward. And it's because we can then capture not only these renewables, but also stranded resources. For example, in the desert, where we got these offshore wind facilities far away from land, and many other things like marine energy, etc. We can also recover some waste streams. We can then have this energy stored for a long period of time at very cheap prices compared to hydrogen, because we don't need to compress it, we don't need to liquefy it, we just need to then have it slightly refrigerated or slightly pressurized. So in terms of long-term 180 days, we're talking about differences of almost 30 times the cost between one and the other. We can also use it for islands and isolated regions. We can employ it as a fertilizer, obviously, as it's been used for over 150 years, but also now as a fuel. It contains, really interestingly, as again, going back to Hans' graphs, more hydrogen than hydrogen itself. And this is because we got another atom. And thinking about molecules, as he mentioned, we got another atom of hydrogen that now plays in this complexity. So in that sense, we got more hydrogen that we can transport in this way, and obviously a very well-developed infrastructure worldwide that accounts almost for 200 billion euros per year that will just move around. You can see here on this other slide, and the other side, right-hand side of my screen, that there are so many different ways and methods to then transport hydrogen from those that are very complex materials to ammonia. And ammonia is the one that shows one of the best properties to do so. So in that sense, again, why not use it? So there are many ways forward to then employ it. And as mentioned before, we got different methods, different ways to then produce it. But there's a point where if we're thinking about using it as a fuel, then we can employ it as in fuel cells. We can use it for transporting internal combustion engines, for heating and cooling, because it's got all those properties as well. Cooling, fantastic cooling properties. It can be burned. We can use it for process industries, propulsion, stationary power. power, and many other applications. One of the things that comes to mind is always, well, how are we going to do that? How are the public are going to react? Do we need the regulations to do so? What are the economics around this? Are the environment going to be better or worse? And then finally, those fundamental things about the combustion of doing so, because it's not that straightforward. So that's the reason, because we have engaged on this subject, and in collaboration with so many other partners, we're trying to solve. And to the question that was just recently asked, and again, just backing up Hans' argument, in terms of zero carbon fuels, the one that shows the greatest energy density is ammonia. When compared to fossil fuels, yes, we do have diesel, petrol, ethanol, etc., that have higher energy densities. But when it comes to then having zero carbon, ammonia compared to hydrogen, even liquid lithium batteries, is much better. Something that as well is really interesting is that when we think about the cost, as I mentioned, moving liquefied or pressurized hydrogen compared to ammonia, is ammonia much cheaper than the other two. And that, thinking about the long distances, either by ship, by rail, or by lorry, that is one of the potential applications that we can use ammonia for. One of the things that is obvious, and again, I would like to raise, is that ammonia and hydrogen in terms of power applications and combustion systems are going to be playing together. It's not that we're going to discard hydrogen completely or we're going to go for ammonia, but they're going to then be complementary to each other. One other thing that I want to mention as well is that when we compare these systems and the renewable energy and how we can then use the final energy to produce power, in comparison with all these different chemicals that we got at hand, that is methane, and that is methanol, ammonia, and also hydrogen, when we just take the whole chain, what happens is that the final efficiency that we can get out of these chemicals is similar in terms of ammonia compared to methane and methanol. But when it comes to hydrogen, because of the high amount of energy and low efficiency that we require for its storage, if we're thinking about cryogenic storage, then it just brings down almost 10% the final efficiency that we can get to then produce electric power. So that's, again, just taking us into another argument of why not ammonia. One of the things, as I mentioned before, again, ammonia is going to be one of the things and chemicals that is going to play an important role, and this is now being said by the International Energy Agency, and it's that we need to then think about a combination of these two chemicals, and it goes as so many studies that now the US have been conducting over the years, and this is just one of the latest, released around 6 months ago, and what they were analyzing were different cities, different situations, where they were assessing hydrogen or ammonia or a combination of both in these locations. And interestingly, you can see in all these scenarios, when you have a combination of both, you have the lowest cost of electricity. And this is very interesting and also obvious, because at the end of the day, if you got some hydrogen that you can use to then power nearby applications of very short trips like fuel cell systems, etc. It makes a nice case of just having some hydrogen to then play around with that. But if you need to store it or transport it, then you need to have the ammonia, in which case then you will have the requirement and then seasonal stranded energy stored for a longer period and lower costs. So therefore, if you have a combination of both, this is what the future might be looking like in terms of combustion and power applications. As I mentioned, ammonia by itself, it might not solve all the problems, but it is going to be part definitely of this combination of mixes of fuels we'll have in the near future. And this has been recognized by many organizations. Again, talking about the International Energy Agency in 2018, they decided to then include into their carriers of energy ammonia. And that was also followed by the European Union, by the UK government, by the Japanese government that has been leading all this agenda around the use of hydrogen and ammonia, Australia and many others. The US, for example, they have just released a new program where they are now looking into the production of a gas turbine and furnaces running on ammonia, and we're talking about $10 million that they just put it into some research and development that they're going to perform doing so. And again, many other economies looking into how we can then make this happen. Just here's some briefing, and probably all of you know as knowledge that you might have around ammonia, all these big programs that are now going ahead in Australia, where we're talking about all the diversification and and delivery of energy from the north to the Southeast Asian region. The CF Plan agreement that was just signed a few months ago to then develop all these green technologies for the production of green ammonia. And then finally, Nuon City that is now announcing Air Products collaboration, a 5 billion renewable hydrogen to ammonia project in Saudi Arabia. And that adds to, for example, what the Japanese have been doing in furnaces, systems, and gas turbines. And recently, just 2 weeks ago, Mitsubishi releasing a communication saying that they're going to run by 2023, 2024, a 40 megawatt power unit running purely on ammonia. And this is the unit that they will be using. So things are happening, things are going ahead, and it's not only in the fertilizing world, it's going to take over as well as part of the energy mix for post production in synthesis and devices for industrial purposes. In our case, what I'm going to approach is out of the 4 different challenges that we got to address when we're talking about ammonia, just the 2 in the middle. So ammonia needs to be carbon free, and we need to then reduce the cost and efficiency being improved, as has been raised by Hans. We need as well to then make it a fuel that allows for power generation at utility scale. We need to then as well acknowledge the public acceptance and the regulations that are required to do so, because otherwise we might have the best technology, but if people don't want to use it, there's no way forward for us. And then finally, the economics that need to be profitable for whoever wants to take over this subject. So for that reason, we have engaged with lots of different partners, and I'll show you now a little bit of what we have been doing, and different subjects that go from chemistry, physics, engineering, biology, social sciences, etc., to develop the technologies that will allow us to do so, and then always think about how we can improve the environment, reduce climate change, avoid emissions, and obviously get profitable, high-efficient systems to do so. So yes, just to give you a hint of what things that we have been doing over the past few years, we were part of the Rutherford Appleton Laboratory demonstrator at Oxford. This was one of the first, if not the first demonstrator to then show the whole chain of production, storage, and consumption of ammonia, and then back to the grid energy that has been worldwide. And we got it at Oxford, Siemens and STFC that is now holding the whole facility. They're always open to then receive people interested in knowing a little bit more about the concept. In our case, what we did was develop the container that hosts the internal combustion engine that is running the power to the ammonia to power part of the system. And this is the engine that we've been using. We convert it, and then instead of just running it on a natural gas that was designed for, what we had to do was redesign it and then allow for blends of ammonia hydrogen to then run it properly. So you can see here on the left side that we started running on some methane, and then eventually we just brought it down. So once that we got it hot enough, we could then just put in all the hydrogen and ammonia to then start producing energy at the same values that we had previously using just pure methane. And as you can see on the other side, we got all these emissions that are going down. Obviously CO2, as we increase the methane fraction, is going up. But when we were running on ammonia hydrogen, obviously zero CO2 CO. Another interesting thing is that NOxes were reduced under those fractions. And this comes as a surprise, and it's got to do with the onboard ammonia that we had into the internal combustion engine, another subject that I'll mention later down the line. Another thing that is interesting, I'm thinking about the techno-economics of all these units, and we've heard a lot about the marine industry now going ahead into development of internal combustion engines that will be run probably in the next couple of years. MAN leading some of these works. How ammonia is going to then play an important role in the following years. But something that again comes back as the techno-economic challenges that we got to surpass before we can do that is that we do have an understanding, as I showed before, of internal combustion engines. We have been using ammonia and hydrogen blends in a successful way, but still producing some emissions that need to be brought down by research and development, but the regulations that are required to do so. And you can see here, for example, compared to some other fuels, diesel, LNG, methanol, etc., where there are some regulations already being imposed by the International Maritime Organization or the ISO standards. In the case of ammonia, we don't have anything yet. And that's, again, something that needs to take us a little bit further, and we need to then put some time to then work on it, and effort worldwide to then make this happen. For boilers and furnaces, ammonia can also be used. In the steel industry, we have the production of loads of this ammonia. For example, in the Arab world, you do have lots of this waste ammonia coming from oil and refineries that has been most of the time flare. And one of the things that can be done is actually recover some of this ammonia, and because it's got enough density, energy density, to then produce power, then produce excess power for your units. And some of the works that we have been doing recently for Tata Steel show that the amount of ammonia that they got and the system that they employ for coke production can actually produce up to 5 megawatts of extra power if we were tapping into that ammonia. Now, one of the things is always the impurities that come with those gases, how to then clean them up, things that, again, we are evaluating with Tata Steel and also with some other partners here in the region that produce cement. In terms of gas turbines, which is the topic that we have been covering for a few years now, let me just start with this really nice assessment that was done recently by Oxford University, and they presented in a UK-India ammonia meeting that we had just a few months ago. You can see here we have two engines, one that is going to be running at 80 megawatts power on the left side. On the right side, we got one that is almost at 870, 90 megawatts. And the interesting thing is that they were evaluating how much hydrogen would be needed if we wanted to run these units. So if we wanted to run, say, for example, for 8 hours, we would need then tube trailers of almost half a ton of hydrogen, and 8 of those. Now, if you wanted to run it for 1 day, you would need then a pipeline of 8 kilometers long to then provide for that energy. If we wanted to run it for 1 week, the small engine of 80 megawatts power, we would need 3 of these NASA super tanks that they use for the shuttle. And if we were thinking about then running for just 1 month, that same unit on pure hydrogen, we would need 4 times these side salt caverns, each of them containing around 810 tons of hydrogen. So obviously, when we go an order of magnitude higher, what happens is that that goes just berserk, completely out of hand. And just thinking about the case of 1 week of running that 870 megawatt power unit, we would need 9 salt caverns just to do so, which is, again, impossible, not feasible, and is just not real. But when we compare it with ammonia, and something that is interesting is because of that energy density that we got available on the amount of hydrogen that we got at hand, then we would need the same amount of, again, capacity if we compare it to then hydrogen. One of these tanks that we use for ammonia that are common practice in the ammonia world, and again, you might have better details about this, can then store almost the same amount of power that we would get from 11 salt caverns of hydrogen. So that means that if we wanted to run the 80 megawatt power unit, then that single container of ammonia can run it up to 3 months. And if we want to run the 870 megawatts unit, it can go for up to 1 week. Just that single anhydrous ammonia tank that we got there, which is, again, fascinating if you compare it with the techno-economics that we got for hydrogen. They did some other extra work on the gas turbine units, and they compared different phases, different cases where we had one splitting entirely the ammonia into hydrogen, another one having a combination of ammonia hydrogen at 70-30%, and then finally using entirely ammonia. So one of the things that they found was that the efficiency finally, because again, as mentioned by Hans, all that energy that we just put it into cracking is going to then be a toll that we need to then take into account into the final production of energy. And just comparing numbers and then using different mechanisms, what they found out was that there was almost an 8% difference between the system efficiency of phase 1 to phase 3. Now, this comes back to then having phase 2. And phase 2 is because we need to have also combustion stability. Phase 3 might be feasible, but it's very difficult to then stabilize an ammonia engine. And this is something that is got to do with the flammability of ammonia that is very dull compared to hydrogen, something that I'll mention right now. When they mentioned and they did some analysis on the levelized cost of electricity using the different platforms and the different phases, you can see how, compared to fossil fuels using green ammonia, as long as it stays at 380 tons dollars per ton, then they have the same kind of numbers and same kind of cost as you would expect from fossil fuels that have some CO2 pricing that might come at some point near the future. So therefore, ammonia, again, just plays a really nice condition, a really nice scenario for the near future, and again, allow us to then think on how we can then do so. Going back to then combustion and that blend that we had in phase 2, why do we want to think about 70-30? Well, the main reason is that the molecule of ammonia, when it burns, is very dull. And also, we have another thing to consider, and is the NOxes that we are going to produce. So for that, we have engaged in a lot of combustion programs and a lot of combustion research. And something that is always interesting is that when you run on enriched fuel conditions, an excess of fuel in your combustor, you get almost 0 or 10 parts per million NOxes at those conditions. And something that we saw as well happening when we were running also with hydrogen ammonia blends is that that is always a trend. And the reason is that what you got is ammonia also being a fantastic denoxing chemical. So ammonia has been used for a long time in diesel engines, in diesel catalytic systems. They have been using for power applications in gas turbines and power plants. Ammonia for decarbonization and denoxing concepts. And this is the same thing that happens inside of a combustor. If you have some excess of fuel, some excess of ammonia inside of those combustors, what happens is that you got some onboard ammonia that is going to then extra burn and recombine with the NOxes that you're producing, and then finally just bring them down to then levels of 10, 20 ppm in units that can have powers of half a few megawatts in power. And this is just talking about concepts that are not still well developed. We haven't talked about any stratified, any increase in temperature, pressurized conditions, anything like that. These are just preliminary analyses that have been done across the world. And again, things that have been performed in Japan, in KAUST, in different organizations all across Europe and in the US. So for that reason, what here we have been developing over these years is this concept of creating new combustors that will allow us to have high stability whilst having very low NOx emissions. And we have been going through a very long path. We are now in the stage where we're setting up and putting everything together in an auxiliary power unit to then demonstrate the concept and then have everything integrated into a cycle. So in the near term, in a couple of years from now, we'll be able to then demonstrate it for combinations of hydrogen and ammonia to then have a stable, high power production with very low NOxes and a reliable energy. Another thing that we have been doing as well is working with our European partners in developing these ideas. We have collaboration that is going on now with the University of Genoa. And what they are doing, they plan to then assess a purely ammonia gas turbine of 300 kilowatts power. Similarly, we're doing research with EDP. And the idea is that we assess some of these blends using ammonia and then cracking some of that to then produce these ammonia hydrogen blends and then finally put it into a large power unit that they got in Portugal. And this again goes into how we can then do so, how we can produce with off-peak power all this ammonia energy, all this ammonia tapping into it, and then once that we require it for peak hours, then just put it back into the engine to produce that excess of energy that we require at that time. So on those lines, we got assessments in cycles that are telling us that if we go with these cooling power heating applications, because we need to remember that ammonia has the incredible property of being a great coolant chemical. So if we use some of that to then improve the efficiencies of our Brighton cycles or our combined cycles, then we can reach efficiencies almost at 60%. And that again goes compared to combined cycle efficiencies of current or newly developed systems of 80% fossil fuel based without any CO2 being involved in the process. So again, it's very reasonable, extremely interesting. And again, just thinking about these concepts without having stratified or more clever smart conditions that we're now evaluating. Similarly, LCA analysis that show that we got then to reduce that and then move forward with that. Propulsion systems is another area that we're looking into it, and then people have been assessing for quite a long time. But it's interestingly now that it's picking up in the recent years. These are some of the graphs that people in Germany, some groups have been developing, and similarly we're thinking about then using some systems to then demonstrate the concept. And as you can see here from the table, you got all these different properties, all these different characteristics that make a fuel more or worse, better or worse to then its counterparts. But interestingly enough, when you have the case of ammonia hydrogen, then you got lots of fives that show excellent performance. The one that always comes to mind is toxicity. toxicity a major issue that we need to deal with when it comes to then power applications. And that's because, again, public perception is a massive issue that we need to take into account. So if someone is just worried about the smell, if someone is worried about the nuisance, and not only that, about the toxicity that it can cause, obviously it's a big problem. And especially when we think about then the potential of having exposure of ammonia, then producing these skin reactions, and even producing particle matter. Something that happens with the chemistry of ammonia is that once they start reacting with some sulfates and nitrates, it starts producing particle matter, something that can go through our skin and potentially just cause us a lot of problems. So on that line of thought, we got the cases of evaluating health and safety issues. We got the cases of public perception. We got the case, for example, of also comparing what happens when we got hydrogen and ammonia. And this case, for example, shows that if we got obviously a hydrogen leak, that is going to then spread immediately, whereas if we got something that is ammonia-based, is going to have a lower sphere of propagation, which again just takes us back to then considering toxicity. Toxicity is the main challenge, and we need to solve it as part of this development. Another thing, before just finishing up, public perception when it comes to then developed or developing countries is completely different. And when we talk about, for example, the case of a developed economy, we did this analysis using the UK and Mexico. They're concerned about the nuisance, the smell of ammonia. Whereas, for example, developing economies, because of the regulations and the restrictions they got that are looser, then what happens is that they are more concerned about these poisonous, toxic characteristics. So again, something that can kill them if there's a release, whereas in the UK, it's going to then smell, someone is going to containing regulations are more important to do so. So public perception is going to play an important part in these developments, and through all the collaborations that we got with many universities, One Cause being our latest collaborator, we got a really nice program going on with them, and we already got some research, interesting things going on in research-based combustion. We have now just reached the conclusions that ammonia can be used for decarbonizing, cooling, heating, power, and propulsion. It's something that needs to be efficiently used, then thinking about low NOxes and then the production of a species that can be recombined to then have an efficient, stable performance. Research is ongoing, and if we want to think about this hydrogen through ammonia economy, we need to start doing it now, as Hans mentioned. We need to then have a combined effort worldwide to then make this happen. Thank you very much. This is a book, just some marketing that I wanted to do of techno-economic challenges that we recently published with Oxford University. And that's it from my side. Thank you very much.